Hello students. We're going to look at question 24, which is in your course package. I believe it's on page 54. We're going to look at how to read through a question like this and answer a question. The main question is trying to determine if there is some dependency between a type of vehicle, between one event and another event occurring. So question 24, we're going to create a data table. Create a data table using Excel. Come on, move over there. And our Excel file. Let's make that a little smaller so you can read things. These questions are always going to have, it's always based on two matrices, two characteristics of something occurring. So we have to read the question first to kind of get an idea of what are the two different types of characteristics. Reading this question is talking about types of vehicles involved in car accidents and whether the vehicle accident is fatal or not. So we're going to look at, we're going to define one type of characteristic as it's a truck or a car involved in the accident, and whether or not there's a fatality or it results in a non-fatality. And we will have totals here as well. And I shall make this a little bigger so everyone can really see it. So as I said, all of the questions are going to deal with two characteristics. It's a 2x2 table, or a table with two characteristics. You could have different types of vehicles listed here and different characteristics listed here as well. So let's start reading this, the data in the question. It says last year's data show that 20% of all hit and run accidents were caused by trucks. So we know that that's a total, 20%. By default, the number of cars involved in an accident is 80%. Figures also show that in 40% of the cases where trucks were involved, the victim was killed. So there's a fatality here. So we can't put 40% there because obviously the total adds up to 20 and this can't be negative. So careful reading of the question basically implies that 40% of the trucks involved in accidents. So it's 40% of 20%. So doing that math, 40% times 20% leaves us 8%. While cases, going back to the question, while cases where cars were involved, only 10% were killed. So 10% of the car accidents resulted in a fatality. So this would be 10% times 80%. So we're left with 8% there. Let's restrict the number of decimal places. That's all the data that's given in the question, but because this is just a 2x2 table, we can fill in the rest. We know that the total for trucks is 20%, so we know that this has to be 12%. The total for cars is 80%, so we know that this is going to be 72%. The total fatalities in all vehicle accidents is 16%. 12 and 20 and 74 is 84%. And hopefully those numbers there, as well as these numbers here, add up to 100%. So sometimes you will be working in a question where you're dealing with percentages. Other times you're working with absolute values. A key indicator here that you're doing everything right is these interior numbers, these joint probabilities, have to add up to 100%. As you can see down here in the lower right area, you get a sum of 100%. So now we can answer some of these questions. 24A, what proportion of hit and runs resulted in the death of the victim? Your answer is right there. 16% of all accidents, 8% from trucks and 8% from cars resulted in fatalities. Now you might be thinking that you have the same probability of being in a fatal accident driving a truck or a car, but because it's not proportional, you know, the values are telling us otherwise, which leads us to part B, trying to determine if type of vehicle and the result of the vehicle are independent. So a test of independence, that's what we want to do in the next to answer the next question. We're going to do that by bringing up a white screen, which I have right there, and keeping these numbers to the side. So a test of independence, this one is pretty open in terms of it's asking you to determine if there's any independence between the type of vehicle and whether or not a victim survives the accident. Other questions might specify determine this test of independence using one of the variables versus another one of the variables. But this one is pretty open. So what we're going to do is I'm going to just pick, let's pick trucks. So know that the probability, oops, what happened there? Let's erase that. The probability of being in a truck accident is 20%. The probability of being in a fatal or being involved in a fatality is 16%. And the probability of the joint probability of being in a truck and a fatality is 8%. So those are the key values you need. In this question, you could pick either truck or car. So I picked truck. You could pick either fatality or non-fatality, and I picked fatality. And then the third value you need is the intersection of those two previous ones you picked. So if you picked car and non-fatality, you would be looking at the joint probability then of 72%. So using these three values, we know that if two things are independent, the probability of truck times the probability of being in a fatal accident will equal that joint probability. So this is our test of independence, seeing if those values are going to actually equal what the observed value is. So I need a little bit more room, so I'm going to have to delete that, and then I shall write out this again just for our reference. So we know that the probability of being in a truck accident is 20%. Being involved in a fatality is 16%. And the big question mark is, do those two things equal the probability of being in a truck and a fatality? And that equals 8%. 20% times 16%, this equals 3.2%. Does that equal 8%? It does not. So because they are not equal, we cannot say that they're independent. So we're going to say, let's just put here, they're not equal, therefore they are not independent. So there is a degree of dependency. So being in a fatality is dependent on the type of vehicle that you are driving. So that's what this data shows, is that the result of an accident, either fatality or non-fatality, is dependent on the type of vehicle that you are driving. So you could do this test with car versus non-fatality, car and fatal, and you're going to get, you won't get the same values we got here, but you're going to get the same final decision, that they are, because they're not equal, they're not independent.